Hi everyone, this is lesson number 11. So today we're going to be talking about the limits of trig and exponential and logs also. Alright, so pause the video and try the do now. The velocity of a particle moves along the x-axis is modeled by a differential equation. So continuous, think of this as continuous. What is the fewest number of times the particle is at rest from 0 to 40? So what do we how many times does it have to? So if you think about it like this, at 0, right, we're at 3. And then at 8 seconds, we're up to 5. And this is velocity. And then we go down to negative 10, up to negative 8, up to negative 4, and then up to 7. So how many times does this hit 0? Twice. So the answer is just 2. Okay, so this is the squeeze theorem. Write this down. In some interval containing C, if the functions f, g, and h satisfy the inequality, then if f and h have the same limit L as x approaches C, then the function g is squeezed to the same limit L as x approaches C. So basically it's saying if h and f have the same limit as we're approaching something, then g has to have the same limit. This is actually a required theorem that you have to learn in calculus. It was actually on the AP test last year. I've never seen that before, so this is an important theorem to know. I think there's another name. I can't remember the other name, but I think there's another name for the squeeze theorem. Okay, so we're going to use the squeeze theorem to prove a limit that we need to know. So let's start with, what is the area of the sector if the angle is x radians? So this sector here, so what would be the area of this whole thing? Well, let's start with what's the area of a circle. The area of a circle is pi r squared. Now this is a unit circle with a radius of 1. So the area of the entire circle is just pi. Now how much of the circle is that? Well, that's x radians out of how many total radians in a circle? 2 pi. So 2 pi times the area of the circle, pi. The pi's cancel. So the area of that sector is x over 2. Right? X over 2 is the area of that sector. All right, so now we're looking at a specific spot on the unit circle. You should have learned these facts last year, that this height is sine, that this height is tangent, and actually this right here is cosine. So you should have learned this last year. So now we're just asking, what's the area of ABD? So ABD, so this triangle. Well, the area of a triangle is 1/2 base times height. What's the base of this triangle? It's a unit circle, so 1, and the height is tan. So that's tan x over 2. So the area of that big triangle is tan of x over 2. What is the area of ABC? So that's this smaller triangle. Sorry, my drawing is really bad. Again, it's the area of a triangle, so 1/2. What's the base? The base is 1 again. What's the height? The height is sine x. So that's sine x over 2. Now, do you agree, looking at this picture, that the sector, I'm gonna try to re-highlight these. The sector, where is it? From here to here, this little pi piece is going to be between the big triangle that's made up of tan, it has all that extra space, and this little blue triangle, we'll do that one in black, the black triangle. So the red is going to be between the green and the black, right? The black triangle is the smallest, then you have the sector, and then you have the green triangle, which has all that empty extra space in it. So based on the squeeze theorem, the area of the small triangle, 1/2 sine x, or sine x over 2, is going to be less than or equal to 1/2 x, which is less than or equal to tan x. And we're talking about from 0 to 2 pi. So we're in quadrant 1. We're not going to worry about any negatives or anything like that. We're in quadrant 1. So now we're going to prove something. First thing we're going to do is get rid of all the 2's, right? Multiply by 2. So I have sine x is less than or equal to x, which is less than or equal to tan x. Right. Now what I'm going to do is going to seem random. I'm going to divide everything by sine. Because we're in quadrant 1 and we can't equal 0, we're allowed to do that. We're not going to have anything weird happen. Sine over sine is 1, less than or equal to x over sine x. Now, tan, I wrote cosine. I think I was thinking of what tan equals. So now this is sine x over cosine x all over sine x. So these signs end up canceling, and we're left with 1 over cosine x. Right. So now I'm going to do something weird. I mean, if this wasn't weird enough for you. We're going to take the reciprocal. But when we take the reciprocal, the inequality flips, right? So the reciprocal of 1 is 1. The reciprocal of x over sine x is sine x over x. The reciprocal of 1 over cosine is cosine. But now the inequalities, instead of being less thans, are now greater thans. I'm actually going to, we can leave it like that. All right, now this is where I want it to be. Now what I want to know is, what's the limit as x approaches 0 of all of these? Well, the limit as x approaches 0 of 1 is just 1. The limit as x approaches 0 of cosine is 1. So now we have this sine x over x. That also has to be 1. So we just proved that the limit as x approaches 0 of sine x over x equals 1. If we plug in 0, we get an indeterminate form. But sine x over x, we don't have some algebraic way of fixing it, so we use the squeeze theorem. All right, so this is our fact. We're going to be using this fact a lot. This is important. So the limit as theta approaches 0 of sine of theta over theta equals 1. And what I tell students last year, we used to, I had them write down sine of happy face over happy face. All right, the limit as theta approaches 0. Because it doesn't always have to be a plane theta. You will see how this changes. All right, so the issue here is sine of the inside, right? The inside is 3 theta. So we need the inside to be on the bottom. I need a 3 in the bottom because it's missing. So if I put a 3 in the bottom, where else do I need a 3? I also need a 3 up top. And remember, one of our rules of limits, if we have a constant, we're allowed to pull it out. So what we really have here is 3 times the limit as theta approaches 0, sine of 3 theta over 3 theta. Now that this and this are the same, we're allowed to say this whole thing is 1. 3 times 1 is 3. So the answer is 3. All right, so that's a simple one where you're just missing a constant. The next one's a little more complicated because if we're using the whole limit as x approaches theta, sine theta over theta, what are we missing? We're missing our thetas. So here's what we're going to do. We're going to divide, we need to put a theta for each of these. And since it's a fraction, remember, what can you do? Whatever I do on the top, I need to do on the bottom. So I'm going to rewrite this as sine of 5, just kidding, sine of 5 theta over theta, all over sine of 2 theta over theta. And this is all the limit as theta approaches 0. So I divided the top and bottom by theta. So now this looks closer to what we want it to be. But now what do we need? We need a 5. I need a 5 here. So then we're going to throw a 5 out front. I need a 2 on the bottom since there's a 2, and a 2 out front. So now the limit of this is 1. The limit of that is 1. So what's our answer? 5 times 1 over 2 times 1. So our answer is 5 over 2. So we were missing a theta. We put it into the problem. Whatever you do to the top of a fraction, you're allowed to do to the bottom. Okay, this is the last one like this. So when you get, there's specific methods for these. So adding in the number, adding in the theta. This one's a little different. What we're going to do here is multiply by the conjugate. What is the conjugate of cosine of theta? Because we need to turn this into a sine. So to turn this into a sine, we're going to multiply by cosine of theta plus 1 on the top and on the bottom. Whatever we do to the top, we do to the bottom. So that means on top, we have cosine squared of theta minus 1 all over theta cosine theta plus 1. Now, I don't see a sign. Do you see a sign? What's the Pythagorean identity involving sine? Sine squared of theta plus cosine squared of theta equals 1. Now, if where can I get cosine squared minus 1? So if I bring this 1 over here, I get cosine squared theta minus 1. And then I have to bring the sine to the other side, so this is negative sine. So that top is actually equal to negative sine of theta over theta. And then what I'm going to do is I'm going to take that bottom piece and I'm going to write 1 over. All right? So I just kind of pulled this piece out, replace cosine squared minus 1 with negative sine. So then the limit here is negative 1 times 1 over, plug in, what do we get? Cosine of 0 is 1 plus 1. So we end up getting negative 1 over 2. These are tricky, I'm not going to lie. These are probably, of all the limit problems, algebraically, these can get weird. I do recognize that these are a little tricky. Okay, so now let's talk about exponentials and logs. So these are actually, these are way easier than what we were just doing. All right, so what is the domain of an exponential? All real numbers. And the domain of a log is 0 to infinity. Please keep in mind the graph of a log in particular. Remember, it looks like that. And this point is 1. So it's negative from 0 to 1, and then it's positive from 1 to infinity. That's an important thing to remember. All right, pause the video. You can do these. These are super easy. All right, number 4. Again, the answer might look weird, but it's okay. We're just plugging in. E to the 10th is e to the 10th. The square root of the ln of 8. Okay, some weird decimal. See this one, e to the 0 sine of 0 minus 3e to the 0. So sine of 0 is 0, e to the 0 is 1, so you just get negative 3. The ln of 1, what's ln of 1 equal to? 0. See, it's literally plugging in. They seem scary, but they're really easy. Like, there's not much to do with these. And that's it. Here is your homework. Have a fabulous day, guys.